Okay, good morning. Well, first of all, thank you very much for the invitation to this meeting. And, well, it's my pleasure to speak to the distinguished young scientists. Well, I'm waiting for my slide to be shown. Okay, yes, thank you. Okay, so today I'm going to talk about neutrino oscillations and small neutrino mass. Well, in fact, I'm an experimental physicist, and well, what we have been doing is just an experiment. Therefore, in spite of this title, I'm going to talk about my experience in neutrino experiments I have carried out. And here, in this slide, you see a photo. And this is the Super-Kamiokande. That is the neutrino detector we have been working on. And actually, this photo was taken last summer. And today, I'm going to talk about neutrino research that were carried out in Kamiokande and Super-Kamiokande. Excuse me, I find, strange. Excuse me. Okay. Oh, no. Yeah. Okay, thank you. No. Oh, yes. Okay, great. So this is the outline of this talk. Well, what I'm going to talk about is neutrinos, but compared with, say, molecules, neutrinos are less familiar to you. Therefore, I'm going to talk about a little bit about the general ideas on neutrinos. Then I want to move on to our experience. First, I'm going to talk about the Kamiokande experiment that was carried out about 35 years ago. Then I move on to the Super-Kamiokande experiment and discovery of neutrino oscillations. And, well, essentially that's all I'm going to talk about. But also I want to briefly mention about the importance of the small neutrino mass, and I'll summarize this talk. Okay, so what are neutrinos? Well, neutrinos are fundamental particles like electrons and quarks. So they are very small particles. And if you ask what are the main features of the neutrinos, then I would say that neutrinos are something like electrons without electric charge. In fact, this feature is very important. For example, because of the no electric charge, neutrinos can easily pass through even the Earth. But fortunately, neutrinos can sometimes interact with matter. Therefore, we are able to study neutrinos. And one more information about neutrinos. Neutrinos, like the other particles, have three types or three flavors, namely electron neutrinos, muon neutrinos, and tau neutrinos. And here I list the matter particles. And you can see at the bottom there are three types of neutrinos. And I want to say that in the very successful standard model of particle physics, neutrinos are assumed to have no mass. Well, of course, this was an assumption. Therefore, physicists have been asking, neutrinos really have no mass. Okay, so this is the background. Now I want to move on to our experiment. Well, the first experiment I was involved was the Kamiokande experiment. Well, I want to tell you the history of the Kamiokande experiment. In fact, about 40 years ago, I would say more than 40 years ago, new theories of elementary particles predicted that protons should decay with the lifetime of about 10 to 30 years. Well, of course, 10 to 30 years is a very long lifetime. Well, in our daily life, even if protons have finite life or not, our daily life doesn't change. But as far as the fundamental physics is concerned, this prediction was very important. Therefore, several proton decay experiments began in the early 80s, and one of them was the Kamiokande experiment. And here is the sketch of the Kamiokande experiment. It was a large water detector. In the deep underground, we constructed a tank of pure water. It has the diameter of 15.5 meters and the height of 16 meters. And it contained 3,000 tons of pure water. And if a proton decays within this water detector, typically 2 or 3 charged particles are emitted. And if these particles propagate in the water, Cherenkov light are emitted. And these photons or light are detected by photodetectors called photomultiplier tubes. And by analyzing these photons, we were able to get the information on the proton decay. That was the idea. And well, of course, in order to do this kind of experiment, we have to construct the experiment detector. So, in the spring of 1983, our members came to the experimental site. That was Kamioka in Japan, in the mountain area. And here you can see a photo. These are the people who constructed the Kamiokande experiment. And in the middle, you can see Professor Koshiba, who was the leader of this experiment. And also, he was the Nobel Prize laureate in physics, 2002. And behind him, you can see 4 young people, students of Professor Koshiba. And these 4 people really worked underground every day for several months. And well, also you notice that we wear safety hat, rubber boots, and so on. This is the style we worked in underground. And well, the actual work in underground was like that. Well, the work we had to do is to install the photomultiplier tubes onto the 3,000-ton water tank. We had to install photomultiplier tubes on the side wall and also top and bottom. As I said, the height of the tank was 16 meters. Therefore, it was non-trivial to install these photodetectors onto the wall. After some discussions, we decided to use rubber boards to install the photodetectors. Well, if we finish installing a layer of photomultiplier tubes, then we raise the water level, then we put the another layer. So this way we worked. Well, as you can imagine, this is not a very efficient way. Well, our floors are not very stable. So we were afraid that we may drop to the water. But fortunately, no one dropped during the construction period. And we finished the construction, and we started the experiment in July 1983. And of course, we wanted to observe proton decays. Initially, we thought that maybe we can observe proton decays every week or every month. Unfortunately, as soon as we started the experiment, we realized that proton lifetime is longer than predicted. Then, after some time, we have to be serious about the background for the proton decay searches. That was the neutrinos. Well, before discussing about the neutrinos, I want to tell you a little bit about the mechanism of generating these neutrinos. Actually, neutrinos are generated in the atmosphere of the Earth. Cosmic ray particles come into the atmosphere from somewhere in the universe. And if they come into the atmosphere, they interact with the air nucleus, producing typically pions. Then these pions are unstable, decay to a muon and the neutrinos. And then a muon is also unstable, therefore they decay to an electron and two neutrinos. And this way, neutrinos are created, and these neutrinos sometimes interact in the Kamiokande detector. And they are the most serious background to the proton decay searches. Now, well, the experiment started in 1983, and in 1986, we still had no evidence for proton decays. But, as I said, with time goes on, we have more and more background of neutrino interactions. Therefore, we have to improve the software to select proton decays rejecting the atmospheric neutrino background events. So in 1986, we tried to improve the software. And with one of them, we wanted to identify if a Cherenkov ring is produced by an electron or a muon. This is a typical Cherenkov ring we observed, and this Cherenkov ring is produced by an electron. And this is another Cherenkov ring. This ring was produced by a muon. So we wanted to separate if these rings are produced by an electron or a muon. Of course, if we write a software, we have to check if the software is functioning properly. Well, typically, if we write new software, we have many bugs. So it's very important to test the software extensively. So we carried out several tests, and as the final test, the neutrino flavor, that is electron neutrino or muon neutrino, was studied for the atmospheric neutrino data so far observed in Kamiokande. Then we found that the number of muon neutrino events was much fewer than expected. Well, as I said, this was a test of the new software, and the result was something wrong. That means that there must be some mistakes somewhere in the software. So we had to find out where is the mistake. And we started various studies to find mistakes. And actually, well, I think in the 80s, we were lucky. We were able to spend a lot of time to study or to find out mistakes. Well, in fact, we worked for about a year to find out mistakes. But we didn't find any serious mistake in the data analysis. So we concluded that muon neutrino deficit cannot be due to any major problem in the data analysis, nor even the simulation. So we decided to write a paper. Well, the paper we wrote at that time was quite simple. We simply reported the number of muon neutrino events observed compared with the expectation. So clearly, data show a significant deficit. And we also did the same thing for electron neutrino events. Then for electron neutrino events, we found that the data and expectations are almost equal. Okay, we simply reported this. Unfortunately, at that time, the world community received this paper rather skeptically. Well, that was unfortunate. But, well, we had studied very seriously if there were any mistake in the analysis. Therefore, we had rather high confidence that what we reported was, in some sense, correct. So, although the community response was not so encouraging, I was excited with the data. But at the same time, I also want to say that we had no clear idea what was the cause of the deficit. Anyway, to me, this data looked so interesting. Therefore, I decided to change my research topic from the proton decay searches to neutrino studies to know what is happening in neutrinos. Well, I said we had no clear idea what was the cause of the deficit. That was true. But at the same time, we thought that maybe, this is just maybe, the deficit could be due to neutrino oscillations. Oh, by the way, of course, you do not know what are neutrino oscillations. So here I want to tell you the essence of neutrino oscillations. If neutrinos have mass, neutrinos change their type or their flavor from one type to the other. For example, muon neutrino could oscillate to tau neutrinos, and here's the typical probability as a function of the neutrino flight length. Here, a muon neutrino is produced. Then, if they begin to propagate in the vacuum, the probability that muon neutrino to remain muon neutrinos goes down. But if they propagate further, the probability come back to unity. If they propagate further, go down, go back, and so on. And when the probability muon neutrino to remain muon neutrino goes down, then at the same time, the probability muon neutrino to tau neutrino is going up. And the total probability is remain to be unity. So this is the neutrino oscillation, and this was theoretically predicted more than 50 years ago. So we thought that maybe neutrino oscillations is the cause of the deficit we observed in Kamiokande. But of course, there are several other possibilities to explain the deficit of the muon neutrinos. Therefore, we wanted to separate neutrino oscillations from the other possibilities. And for this, we thought this way. I said neutrinos are produced by cosmic ray interactions in the atmosphere. That means neutrinos are produced everywhere in the atmosphere, and some of them are produced just above us, typically 10 to 20 kilometers above us. And these neutrinos, after traveling 10 to 20 kilometers, come to the detector. So they travel only 10 to 20 kilometers. This could be a short distance. Therefore, these neutrinos may have no time to oscillate. However, neutrinos created in the other side of the Earth, they have to travel long distances, typically 10,000 kilometers. So this is a long distance. Therefore, these neutrinos may have a possibility to change their flavor by neutrino oscillations. So we thought that this could be a very important key measurement to tell us if neutrinos really oscillate or not. So we thought we should observe up versus down asymmetry of the atmospheric neutrino flux. Unfortunately, well, of course, this was the idea, but unfortunately, the Kamiokande 3,000-ton detector was too small to observe this effect. Well, because Kamiokande detector was too small, the number of neutrino interactions that Kamiokande was able to observe was too small to really get the statistically meaningful result. Therefore, we needed much larger detector. That was the Super-Kamiokande detector. Now, I want to move on to the discovery of neutrino oscillations in Super-Kamiokande. As I said, we needed much larger detector, and Super-Kamiokande is a 50,000-ton water Cherenkov detector, which is about 20 times larger than the original Kamiokande experiment. It has a diameter of about 40 meters, and height is also about 40 meters. And this detector is located 1 kilometer deep underground. By the way, of course, this is an international collaboration. At present, we have about 170 collaborators from 10 countries. The initial idea of the Super-Kamiokande experiment was proposed by Professor Koshiba in 1983. The Japanese government approved the project in 1991, and the construction period was for 5 years. And in the last year of the construction, our collaborators came to Kamioka to install the photodetectors onto the detector tank, as we did in Kamiokande. But, of course, Super-Kamiokande is much larger. Therefore, the installation of the photomultiplier tubes onto the detector tank was much time-consuming and manpower-consuming. So, the Super-Kamiokande collaborators worked underground in 1995 for almost 1 year. This photo was taken in the spring of 1995, where we installed the photomultiplier tubes onto the top or roof of the Super-Kamiokande detector at the bottom. Anyway, I'd like to show this photo because typically these many people worked in underground for about 1 year. And I would say about, 80% of these people are the Super-Kamiokande collaborators. So we really worked in underground for almost 1 year. By the way, I said we installed the photomultipliers for the roof at the bottom. In fact, after finishing the installation, the whole structure, roof structure, was raised from the bottom to the top. The structure had 300 tons, and therefore this operation was non-trivial, and of course, we physicists cannot do that. So we asked the special company to do that. Anyway, the construction of the Super-Kamiokande experiment went well, and in January '96, we started filling pure water into the Super-Kamiokande tank. This photo was taken from the top of the tank, viewing the inside, and you can see the water level is almost half of the whole tank. And the experiment began in April 1996. And well, I think we had the experiences of the water Cherenkov detector in the previous generation experiment. And therefore, the data taking in the Super-Kamiokande experiment went well from the beginning. So from the beginning of the experiment, we observed these neutrino interactions. This is a typical electron-neutrino interaction, and this is a typical mu-neutrino interaction. So we observe these neutrino interactions every day, well, typically 10 events per day. And we analyzed these data as a team. As I said, we have about 100 collaborators, and we knew when we started the experiment that neutrinos could be quite interesting. Therefore, we formed a team to analyze the neutrino interactions, and we worked together to get the science result as soon as possible. And in fact, I think we were extremely successful. In 2 years, we were able to announce the first major result from Super-Kamiokande. The result was presented at the Neutrino conference in '98. And here I show you one of the slides we presented at the conference. By the way, so far I have presented my speech based on PowerPoint, but 20 years ago, the technology was different. Well, we copied our data onto a plastic film, and we wrote down several comments and showed this plastic film by a projector. And that way, we presented our result. But, well, the reason I'm showing this slide is because this is very important. So the upper one is the electron-neutrino interactions, and the lower one is the mu-neutrino interactions. And the most important thing is this horizontal axis. This is the direction distribution. 1 means downgoing neutrinos, -1 means upward-going neutrinos, neutrinos coming from the other side of the Earth. Of course, 0 means neutrinos coming from horizon. Then you notice for downgoing neutrinos, downgoing muon-neutrinos, the data points which are dots with error bars are in good agreement with the prediction which is shown by shaded box. But if you look at the upward-going neutrinos, data have a significant deficit, almost a factor of 2 deficit compared with prediction. So this data can be clearly explained if we assume neutrino oscillations. That means mu-neutrinos created in the other side of the Earth while propagating in the Earth, they change their type, their flavor. And when they arrived at the Super-Kamiokande detector, the probability that mu-neutrino remain to mu-neutrino is essentially half. This way, we convinced the neutrino community, global neutrino community, that neutrinos oscillate. Well, as I said, we presented this result at the conference. But I think we are very fortunate because on the next day, President Clinton gave a talk at MIT's 98 commencement. Of course, this is a long talk, but in the middle, he mentioned about our experiment. And, well, let me repeat what he said. Just yesterday in Japan, physicists announced a discovery that tiny neutrinos have mass. Now, that may not mean much to most Americans, but it may change our most fundamental theories from the nature of the smallest subatomic particles to how the universe itself works, and indeed how it expands. Well, we were delighted to hear these kind of words, but furthermore, he said, the larger issue is that these kinds of findings have implications that are not limited to the laboratory. They affect the whole of society, not only our economy, but our very view of life, our understanding of our relations with others, and our place in time. So we were really honored to hear this kind of remark from the US president. I'm wondering, what will be the president's remark if the discovery was now? Okay, anyway, this was our work. And so far, I only explained our experimental work. But you may ask, why the neutrino mass is so important? Well, quarks have mass, electrons have mass. Why neutrino mass is so important? Well, still we think neutrino mass is important. So I'd like to convince you why we think that neutrino mass is important. Here, I show you the mass of quarks and charged leptons, including electrons. There are 6 types of quarks and 3 types of charged leptons. They are shown here. Their masses are shown there. Now, the discovery of neutrino oscillation was 20 years ago, and after that, the world neutrino community has been studying neutrino oscillations and neutrino mass very seriously. Now, we have a much better idea what are the neutrino mass compared with 20 years ago. So here, I want to show you the estimate of the neutrino mass based on the experimental data. They are here. So clearly, you notice that neutrino masses are plotted in a rather different place in this plot. And I want to ask you to be careful about the horizontal axis. Here, the horizontal axis have the unit. This 1 unit is 100. So if there's 2 unit separation, that means mass is different by 10,000. So if the separation is 5 units, that means the mass is different by 10 billion. So clearly, this figure tells us that neutrino masses are approximately, or even more than, 10 billion or 10 orders of magnitude smaller than the corresponding masses of quarks and charged leptons. 10 orders of magnitude or more. The present mechanism to generate the particle mass cannot explain this kind of small neutrino mass. Therefore, we believe this is the key to better understand elementary particles and the universe. Therefore, we are excited with the neutrino mass. Well, of course, the present particle physics cannot explain these small neutrino mass. Therefore, it's very important for our better understanding elementary particles. But also, I wrote universe here. Why the neutrino masses are related to the universe? Well, actually, for this point, we are not sure, but we think maybe, well, at this point, just maybe neutrino masses are the key for us to understand the big mystery in the universe. Well, here I show you a photo of the far universe. You can see many galaxies or maybe stars. And one thing we know is these galaxies and stars are made of matter. Well, somehow we do not understand why the universe is made of matter. You may think strange, but if we consider the Big Bang universe, we find out that we do not understand. In the Big Bang universe, the temperature of the universe was extremely high. And in the extremely high temperature Big Bang universe, always particles and antiparticles were created simultaneously. And therefore, the number of particles and number of antiparticles should have been equal in the Big Bang universe. But in the cooled down present-day universe, we only see matter particles. Why? Well, actually, in a sense, we understand what happened. In the Big Bang universe, number of matter particles were, say, 1 billion 1. On the other hand, number of antiparticles were 1 billion. They were almost equal. Then, if with the universe cools down, if particles and antiparticles meet, they annihilate, disappear. Therefore, at present, we have this one in our universe. That is us. That is our galaxy. That is our star. So this way, we understand. But in fact, this is cheating. I said there should have been equal number of matter particles and antimatter particles. Well, of course, 1 billion 1 is almost equal to 1 billion, but they are different. So we have to understand why there was this extra 1. And in fact, we do not understand why there existed this extra 1. But we think that maybe neutrinos with very small mass might be the key to understand this big mystery of the universe. So therefore, we are excited. Neutrinos may be the key to understand this big mystery. But this is still maybe. We have to check if this idea is correct. And therefore, the world neutrino community is planning the next stage of the neutrino research. We'd like to know if neutrinos are related to the origin of the matter in the universe. I'm not going into detail of these experiments, but these are the Neutrino Oscillation experiment, next generation. And with these experiments, we'd like to study if neutrinos are related to the origin of the matter in the universe. By the way, well, why we need the next generation experiments? Because the present-day experiments are not powerful enough to understand this big question. And next generation experiments, we need a much better and bigger detector than the present-day experiment. For example, in Japan, we are thinking about the next generation experiment, and that is going to be actually almost a factor of, say, 5 to 10 bigger than the present Super-Kamiokande experiment. Anyway, we are excited we could understand the origin of the matter in the universe. Okay, let me summarize. Atmospheric neutrino deficit was observed by proton decay experiments unexpectedly. That was in the 80s and 90s. Subsequently, in 1998, Super-Kamiokande discovered neutrino oscillations, which shows that neutrinos have mass. And the discovery of non-zero neutrino mass opened the window to study physics beyond the standard model of particle physics. And neutrinos with small mass might also be the key to understand the fundamental questions of the universe. And I feel that I was very fortunate. I had very good advisors, colleagues, and I was involved in very good projects. So, from my experience, my final words to you is, if we work hard, and if we are lucky, nature kindly tells us the secret of it. So, let's work hard. That's all. Thank you very much.